Assalamualaikum and salam sejahtera I bid to the panelists of my final year project 2. My name is Afrina Binti Zubil. My matric number is 2018264642. My supervisor is Rosnadiah binti Bahsan. Co-supervisor is Dr. Engineer Al-Hassan Salami Tijani. Today I'm going to present my final year project 2. The title for the project is Numerical Investigation of Fluid Flow and Convective Heat Transfer Characteristic of Heat Sink with Variable Geometrical Configuration.
In this presentation, we will discuss about introduction, literature review, methodology, result and discussion, and conclusion of the study.
In this study, we will discuss about heat sink. So, what is heat sink? Okay, heat sink is the type of cooling mechanism that acts as heat exchanger. So, heat sink will dissipate the heat that was generated by electronic device. Thus, in this project is to investigate the heat sink design with a better thermal performance as cooling mechanism. The example of heat sink application is in the CPU, laptop. In vehicle, we have radiator and also handphone. There are two objectives for this study. The first one is to identify the heat transfer characteristic for three different geometry configuration of heat sink that was designed. Second is to validate the simulation result with experimental data from the literature. For these past few decades, the advanced technology has affected the development of electronic device, which the device was designed in a compact and small size. For example, smartphone and laptop. Overheating of this device is triggered by the electricity that running through the device when it processes data. And it also will release heat in the device. Then, when there is an excessive heat generated, and it is beyond the safe limit of the electronic device, it can reduce the performance, reduce lifespan, cause damage like explosion and logic error to the device. Thus, to maintain the device performance in all conditions, the waste heat must be removed by using the effective cooling method. The scope of work in this study is, the first one is modeling the heat sink design using CATIA software. Second, undergo simulation by using computational fluid dynamics software, that is ANSYS R16 Fluent software. And the last one is analyze the result of thermal characteristic of every design. This study was conducted based on the previous research. The first one is from Frega et al. It said that plate fin heat sink with fillet profile remove more heat compared to the traditional design. Next, Tari et al. Found that the rectangular and circular perforation has lower pressure drop compared to the plain heat sink. After that, Zhu et al. These studies found that the groove will increase the flow area and reduce the pressure drop. After that, Zaretaba et al. Found that forced convection can increase the heat transfer coefficient and enhance the heat transfer from the surface. Last one is Huang et al. It discussed about tree-shaped microchannel heat sink and found that the branching channel has a lower pressure drop and lower Nusselt number. Next is methodology. There are 6 processes in this study, starting from geometrical modeling, CFD analysis, meshing geometry simulation, setup and boundary condition, convergent analysis, and the last one is calculation procedure. The first methodology is geometrical modeling. There are 3 heatsink geometry for this study. For this modeling process, the heatsink model was designed by using CATIA software. The first design, as shown above, is called pin-fin heat sink with rectangular perforation. This design has 10 rectangular pin-fin between each plate fin. Then, for each pin-fin, there are 4 rectangular perforations. This is the second design. This design called pin-fin heat sink with circular perforation. This design is same as the first design, but the difference is this design has circular perforation at the pin fin. This is the third design. This design called pin fin heat sink with groove. As you can see, this design doesn't have any rectangular pin fin as design 1 and design 2. So, this design only has groove inside the plate fin. And then this show the design of the groove, that is 3-shape design. Next process is computational fluid dynamic analysis. In this process, the heat sink will be placed inside the rectangular domain. This shows the rectangular domain. The function of rectangular domain is for the fluid flow throughout the heat sink. In the table shows the dimension of the domain, where the length is 160 mm, height is 25 mm, width is 39.7 mm, and the length from the domain to the heat sink at both sides is 60 mm. The third process is meshing geometry. Meshing is the discretization process of complex geometry into simple elements. Heat sink geometry that was modeled in the CATIA as shown in figure A will be divided into simple elements like in figure B. Meshing process will affect 3 things, that is speed, conversion of computational, and then accuracy. This is because the finer the set of mesh or number of grid will produce accurate result, but it requires longer computational time and need a longer memory to run the simulation. For this geometry, it was discretized into tetrahedral grid. The next process is simulation setup and boundary condition. So the table shows the boundary condition and the assumption that was applied in the study. The first one is the fluid flow is steady and incompressible. Second, the fluid volume is the size of the domain for each heat sink's design. The heat sink's material that was used is aluminium. The heat flux that was applied at the bottom part of the heat sink is 18,750 watt per meter square. The inlet velocity of the fluid is set at 2 meter per second to 6 meter per second. The air temperature was set at the inlet is 25 degrees Celsius, that is equal to 298 Kelvin. The number of elements that was analyzed is between 1 to 4 million elements. And then the turbulent model that was used is K epsilon RNG. The last one is the pressure velocity coupling, that is simple model. Next is convergent analysis process. Convergent analysis is the process to choose the suitable turbulence method for the simulation. There are 6 turbulent models that was tested in this process. The table shows the result obtained from the simulation for the turbulent method. Based on the table, shows that the K epsilon RNG has the lowest velocity error compared to other model. Thus, this model was used in this study for the heat sink simulation. The last process is calculation process. This table shows the equation that was used in this study to calculate the thermal performance and numerical analysis of the heat sink. The equation that was used is Nusselt number, heat transfer coefficient, convective heat transfer, rate of heat energy, mass flow rate, Reynolds number, hydraulic diameter, thermal resistance, pressure drop, and area for all heat sink. Firstly, for this section, let's recap on the geometry meshing slide shows how the geometry was divided into many small elements. A finer mesh will affect the accuracy, the simulation speed, and then the conversion of computational. So, this grid independent test is the process to find the optimum grid of the proper concentration with suitable computing time. As you can see, the table shows the result from the grid independent test for 5 different number of elements. From these 5 simulation set shows that the third set of elements has the smallest error of velocity compared to other set of elements. This can be concluded that at the third point of element, the set is dependent where it can reduce the simulation time and lower memory needed with an accurate result. Hence, the third mesh is chosen for the further simulation. Next is the validation of numerical computation. Validation process is to verify the accuracy of the data obtained with the previous research from R.C. Adhikari et al. So, the CFD simulation was carried out in this study to determine the temperature difference, Nusselt number, and Reynolds number at different convective heat transfer. The validation was conducted by using the same boundary condition and assumption as the research. This 4 table shows the result for the temperature difference between the simulation and the previous data for 4 different convective heat transfer value. To know the validity of the result, the percentage error was calculated by using the mean absolute percentage error equation. So, as you can see, each simulation has lower than 10% of percentage error. These 2 graphs shows the comparison of simulation result and experimental data by R.C. Adhikari et al. So, figure A shows the result comparison between the air velocity and temperature difference at different convective heat transfer. Then, figure B shows the comparison between the Reynolds number and Nusselt number at different convective heat transfer. Based on the compared result, the numerical computation and experimental from the previous study shows that the value are close to each other. And then as we can see, the slide before shows the percentage error is less than 10%, which means this validation is acceptable. Next, we move to the thermal performance of heat sink. These 2 graphs shows the comparison of thermal performance for all 3 heat sink designs with air velocity. Graph A shows the comparison between the base temperature versus air velocity. From this graph shows that when the value of air velocity increase from 2 meter per second to 6 meter per second, the base temperature of heat sink will decrease. Thus, pin-fin heat sink with rectangular perforation has the lowest base temperature compared to other design. When the base temperature is low, the heat sink tend to produce the air with lower temperature because we need to reduce the temperature of the electronic device. Then, graph B shows the pressure drop of 3 heat sinks. It shows that when the air velocity increase, the pressure drop in the heat sink will increase. It shows that the pin-fin heat sink with groove has the lowest pressure drop compared to other design. This pressure drop is one of the important parameters to choose the effective heat sink. This is because when the pressure drop is small, the pumping power to force the fluid to the heat sink is less. It also will save the power consumption toward the heat sink application. Next is the thermal performance for all 3 heat sinks with respect to Reynolds number. Graph A shows the comparison between the base temperature versus Reynolds number. From this graph shows when the value of Reynolds number increase, the base temperature for all 3 heat sinks design will decrease. From this graph, pin-fin heatsink with rectangular perforation has the lower base temperature as respect to Reynolds number. Then, graph B shows the pressure drop of 3 heatsink. It shows that when the value of Reynolds number increase, all the pressure drop for the heatsink will increase. The pin-fin heatsink with groove has the lowest pressure drop compared to other design of heatsink. Next, graph C shows the comparison of heat transfer coefficient of 3 design. From the graph, it shows that when the Reynolds number increase, the value of heat transfer coefficient will increase. Then, design for pin-fin heatsink with circular perforation has the highest heat transfer coefficient. This shows that this design tends to transfer heat faster compared to the pin-fin heatsink with rectangular perforation and pin-fin heatsink with groove. Lastly, graph D shows that the comparison of Nusselt number with Reynolds number. If the Nusselt number is higher, it tends to release heat more compared to the lower Nusselt number. We can see from this equation, where when the value of Nusselt number increase, the value for the heat transfer coefficient will increase. Thus, from this graph, it shows that the pin-fin heatsink with circular perforation has the higher Nusselt number. Next is the efficiency of the 3 heatsink design. The efficiency was calculated by using this formula. So from the graph, all the design were found to increase with respect to the Reynolds number. However, the response of efficiency for the rectangular and circular perforation with respect to the Reynolds number is very small, whereas for the groove design has a sharp increase in Reynolds number. This is because the effect of groove surface will enhance the Nusselt number, which this will increase in efficiency. Next is the temperature contour. By visualizing the temperature contour of different heatsink geometry, it can be seen how the distribution of temperature in the heatsink will affect the temperature of the airflow throughout the heatsink. Figure A to C visualize the temperature contour of the base and pin-fin for each heatsink design. From the design of figure A, that is for pin-fin heatsink with rectangular perforation, shows that the temperature start to increase at the 5th row of the pin-fin, compared to the figure B, that is for circular perforation, where the temperature start to increase at the 4th row of the pin-fin. After that, for the figure C, that is for pin-fin heatsink with groove, shows that the temperature start to increase when the air reach the half of the heatsink length. Therefore, the highest temperature for each heatsink is shown in the yellow box at the slide. Moreover, it shows that the higher the surface contact with the air, the lower the base temperature can be reached, which proof from the pin-fin heatsink with rectangular perforation design. Next is pressure contour. So, from the pressure contour of the 3 heatsink design, it shows that the pin-fin heatsink with rectangular perforation has the highest pressure at the heatsink compared to the pin-fin heatsink with circular perforation and pin-fin heatsink with groove. The pressure was affected because of the resistance from the extended fin, perforation and the groove. Therefore, it shows that when the higher the resistance for the airflow, the higher the pressure will occur at the heatsink. Next section is velocity contour. Figure A to C shows the velocity profile in vector at 3 different designs of heatsink. As you can see, every heatsink has 3 planes at 10 mm, 15 mm and 20 mm height from the heatsink base. It can be observed that the velocity increases along the flow direction for all the design cases. However, the velocity increase sharply across each fin plate, and vector formation appear to be present around each fin. The fin heatsink with groove has the highest velocity profile. This is because the presence of the groove. The presence of the rectangular and circular perforation for pin fin heatsink with rectangular perforation and pin fin heatsink with circular perforation respectively slow down the velocity of the fluid, and this is the cause of lower velocity profile for the pin fin heatsink with rectangular perforation and pin fin heatsink with circular perforation. This is the velocity contour that is in streamline pattern. From figure A to C, visualize the streamline pattern for velocity profile for each heatsink design. This simulation is to observe the air movement through the heatsink, where the air will flow from the resistance that is pin fin, due to seek the pass without resistance. Moreover, figure C, that is pin fin heatsink with groove, shows a better streamline compared to the pin fin heatsink with rectangular and circular perforation. This is because the streamline of the airflow out from the pin fin heatsink with groove is higher compared to the pin fin heatsink with circular and rectangular perforation. From this simulation shows that the higher the resistance, the airflow throughout the heatsink will decrease. The conclusion from this study is the research carried out has been successfully met the goal of this project. Then, the higher the resistance in the heatsink, such as the presence of pin fin or perforation, it can reduce the temperature of the fluid. It shows that the pin fin heatsink with rectangular perforation has this type of criteria. Next, the lower the pressure drop also play a big role in enhancing the heat transfer performance, that is for pin fin heatsink with groove. The last one, the design for pin fin heatsink with circular perforation has the highest heat transfer coefficient. This shows that this design tends to transfer heat faster compared to the pin fin heatsink with rectangular perforation and pin fin heatsink with groove design. So that's all the presentation for my final year project 2. Anyone who has any question regarding my presentation, you guys can contact me through the email or my phone number. Thank you.